In problem 13, we have a boat sitting on the top of the water. Okay, I guess I should make my water blue. And here's the boat sitting on top of the water. Sailboat. Got an anchor. That's how deep? It's 25 feet deep. Dare I draw an anchor? Okay, I'll try something like this. There's your anchor, 25 feet deep. And you want to pull this anchor up with your little pulley here to the top of the water and into the boat. Okay, we're gonna figure out the work done to pull the anchor up to the surface of the water instead of all the way into the boat. The anchor weighs 100 pounds in the water at least. If it was out of the water, I guess it should weigh more, right? Because in the water, it's got a little bit of buoyancy to it, though it's an anchor, so maybe not much buoyancy. It's not like it's a feather or something. So it probably weighs a little bit more when it's out of the water, but here in the water, it weighs 100 pounds. In this case, because we're pulling it up to the top, the total work done is the work done pulling the anchor up, and also it's not a rope, it's a chain. It's a chain here, upward. The chain does have a mass or weight density of 3 pounds per foot. And this is easier than the example on Wednesday because we're pulling it all the way to the top. The thing that was confusing on Wednesday's example was it was 75 feet and we only pulled the bucket part way up, not all the way up. And that's where I got confused when I worked through that problem. But this ends up being easier. For the anchor, the work done is indeed the force times the distance, F times D. The force is the same as the weight, 100 pounds. The distance is 25 feet. I am doing a simplification and imagining that anchor to be just like 1 point, even though it's, of course, not. That's a simplifying problem-solving technique. Giving you, what, 2,500 foot-pounds, technically foot times pounds, but people often put a dash there, but it's not a subtraction, it's a multiplication. So that's for the anchor itself. What about the chain? It depends on where you are. What small chunk are you thinking about? If you're talking about a small chunk that's near the surface to begin with, it doesn't have to go as far as a small chunk near the bottom. D is not constant along the chain. For a given distance of small chunk or length, delta y, F is constant, but D changes. I'll write W for the chain. Initially, we'll write question marks. It's good. We're going to have to do an integral. Think about the small chunk here. What's the small amount of work required to raise that small chunk to the surface of the water? It would be a small amount of weight, delta F. F is the weight, because weight is a force against gravity. It's a small weight because it's a small chunk, times the distance. The small weight is the weight density, 3 pounds per foot, times the number of feet of the chunk, the small length, delta y feet. The distance is approximately, well, if this is y, then this would be 20 minus y, or 25 minus y, excuse me. The distance is approximately 25 minus y. That would be in feet. Here, the feet would cancel. Your final answer for the small work done is you rearrange 3 times 25 minus y times delta y foot-pounds. Work done for the small chunk at approximate height above the surface or above the bottom of the lake, say y. Total work is the sum of the small works, which will be approximately, and by the way, this was an approximation here, because this 25 minus y was approximate. Approximately a sum of these things. Hopefully by now you're at the point where you say, hey, that's a Riemann sum for that function. That's the function that I've got to integrate. I let delta y go to 0. The total work done is going to be the integral of 3 times 25 minus y dy. Limits of integration. Y is the distance from the bottom of the lake to the top of the surface of the water. Y does start out at 0, talking about chain chunks that are close to the bottom, and goes up to 25. Right? Certainly that's easy enough to do by hand, but let's, for the sake of quickness for the rest of class, do all our integrals in Mathematica. Integral from 0 to 25, 3 times 25 minus y. 937.5 foot-pounds. You should make sure you can verify that by hand. Final answer then is to add 2,500 to that. Percent sign plus 2,500 gives the final answer of 3,437.5 foot-pounds. What if I had taken y to be something different? Instead of the distance to the bottom of the lake, what if I had taken y to be the distance to the surface of the water? Then this distance here would have been y instead of 25 minus y. Y would still go from 0 to 25, 0 corresponding to the surface of the water, 25 corresponding to the bottom. I'd still do an integral from 0 to 25, but it would be a different integral. Replace 25 minus y with y. It's got to be the same final answer, though. And it is 937.5 for the integral. So even though the integral is technically different, both of them give you the right answer.